I had the privilege of working with the late Professor Mark Burgin since 2015, studying his pioneering work on the general theory of information, GTI. Just a week before his passing on February 18, 2023, we engaged in deep discussions about a paper we were co-authoring. What a legacy he has left behind. This presentation is dedicated to exploring the application of GTI in the design and development of intelligent machines exhibiting autopoietic and metacognitive behaviors. GTI serves as a unifying conceptual framework that bridges three fundamental realms of existence: the material, the mental, and the digital. Professor Burgin's work provides a powerful lens through which we can understand how information operates and evolves across these domains. In this talk, we will examine the intricate relationships among matter, energy, information, and knowledge, focusing on three key themes. The connection between the material and the mental, how the physical world composed of matter and energy relates to the mental worlds of biological systems. The role of ideal structures, how these structures form the foundational connective tissue of reality and its mental perception, etched into the observer's mind as semantic and episodic memory from cradle to grave. Knowledge structures and intelligent behavior, how these structures underpin and explain autopoietic and metacognitive behaviors in both carbon-based biological organisms and silicon-based digital machines. We will illustrate the practical application of GTI through two concrete examples. A distributed video-on-demand service. Imagine a system that not only delivers content but also learns from user behavior, adapts its delivery mechanisms, and optimizes itself in real time. GTI provides the theoretical foundation for such a purpose-driven, adaptive, and intelligent distributed software system. A medical knowledge-based digital assistant. This assistant goes beyond simple information retrieval. It understands the context of a patient's condition, bridges the knowledge gap between patients and healthcare providers, and evolves its knowledge base through continuous interaction. GTI enables this kind of dynamic, context-aware intelligence. The material world is made up of matter and energy. Its structure, how it functions, and how it changes over time are all shaped by the transformation of matter and energy, following the fundamental laws of nature. A system's structure, its parts and how they interact determines what it does. As energy and matter change, systems evolve, always under the guidance of natural laws. All physical systems follow the laws of thermodynamics. Their energy and entropy, a measure of disorder or randomness, are closely tied to their structure and play a key role in determining how the system behaves. This behavior often appears as exchanges of energy and entropy with the environment. Understanding how systems manage energy and entropy is essential to understanding how they work and change. Information helps describe a system's state, structure, and behavior over time. Interactions between a system's parts driven by events involving matter and energy tend to move the system toward more stable, lower energy states. These changes happen within a space of possible states, known as phase space. The structure of this space and how it evolves over time can be described using what's called ontological information. In short, material systems are defined by their energy and entropy. The interactions that drive changes in these properties and thus the system's behavior are governed by the universal laws of nature. The human genome encodes the blueprint for organizing a society of cells into a self-regulating, cognitive system: body, brain, and mind capable of sensing, interpreting, and acting upon the world. Through sensory interfaces and memory systems, this biological architecture enables continuous knowledge updating and reflective cognition. The general theory of information, GTI, offers a formal framework to explain how such systems exhibit autopoietic and metacognitive behaviors. Mental structures utilize knowledge stored in semantic and episodic memory through two primary mechanisms. The first is pattern learning and mimicry, where behaviors are reinforced based on the success of predicted outcomes, an adaptive, feedback-driven process. The second is to create mental models, which are internal representations that help organisms understand and interact with the world. These models are built and refined through three types of reasoning: induction, learning general rules from specific experiences; deduction, applying known rules to predict outcomes; and abduction, inferring the most likely explanation from incomplete information. Together, these reasoning strategies enable adaptive thinking, allowing organisms to simulate, plan, and act effectively without relying solely on trial and error learning. Information encodes the phase space of material structures and their evolution, shaped by the dynamic interplay between energy and matter. Information carriers such as signals, molecules, or symbols contain structured descriptions of these material configurations. Biological systems are uniquely capable of receiving, processing, and generating internal representations, mental structures that serve as models of the external world. These internal models organize and represent knowledge, enabling the system to interpret, categorize, and relate incoming information in meaningful ways. Through this process, biological systems construct a coherent understanding of their environment, which guides perception, decision-making, and adaptive behavior. Biological cognition is driven by purpose-oriented, autopoietic, and cognitive knowledge structures. These structures are both genetically encoded and experientially learned, wired through genes and refined through neural networks. According to Hebbian principles, neurons that fire together, wire together. These networks self-organize through repeated activation patterns to form stable circuits that underpin behavior. These knowledge structures support two major forms of memory. Semantic memory encodes facts, concepts, and general knowledge about the world. Episodic memory encodes personal experiences and specific events in time and space. Together, these systems enable organisms to interpret their environment, predict outcomes, and execute adaptive behaviors in alignment with internal goals and external demands. Mental structures are internal representations formed through both innate mechanisms and experiential learning, serve as the cognitive scaffolding for higher-order functions such as reasoning, learning, and problem-solving. These structures enable inference, drawing conclusions from known information by applying logical or probabilistic rules. Pattern recognition, identifying regularities and structures in sensory input or abstract data. Abstraction, generalizing from specific instances to broader concepts, enabling flexible thinking and transfer of knowledge across contexts. By organizing knowledge into interconnected schemas, mental structures allow biological systems to simulate possible futures, evaluate alternatives, and adapt behavior in complex, dynamic environments. Mental structures guide decision-making and adaptive behavior by synthesizing past experiences, interpreting the current context, and projecting future goals. Through this integration, they generate coherent strategies that enable organisms to respond flexibly and effectively to dynamic environments. The Burgin-Michelini thesis, BM thesis. Artificial cognitive systems must operate on three levels of information processing. Physical level, hardware and infrastructure providing resources for software execution, metabolism. Logical level, algorithms and data structures providing replaceable software. Knowledge level, semantic understanding and decision-making. These systems should be modeled using triadic automata, which extend traditional automata theory to include self-regulation, adaptation, and learning. Resulting systems are teleonomic, purpose-driven, autopoietic, meaning they can self-organize, self-maintain, and evolve similar to biological organisms. A digital genome is a framework for building, operating, and maintaining distributed software systems. Mimics biological systems by encoding behavior and structure in a genome-like format. Uses associative memory to store and retrieve patterns based on context, not just exact matches. Maintains an event-driven interaction history, allowing systems to adapt based on past experiences and interactions. This approach enables context-aware decision-making, self-regulation of distributed components, dynamic adaptation to changing environments, enhanced autonomy. Systems can evolve and adapt without constant human intervention. Event-driven memory allows systems to learn from failures and successes. Moving beyond rule-based AI to systems that understand and reason. Useful in edge computing, IoT, and cloud-native applications. This slide gives an overview of how traditional computing systems are structured and how they work. It focuses on three main types of architectures: symbolic, subsymbolic, and hybrid. At the core, all of these systems are based on algorithms. That means they follow a set of instructions to move from one state to another. In symbolic systems, both the data and the operations are represented using symbols like words, numbers, or logic rules. These systems are great for tasks that are clearly defined and rule-based, like solving equations or running expert systems. Subsymbolic systems, on the other hand, work more like the human brain. They use neural networks that learn from data like images, sounds, or text by adjusting internal parameters. Instead of following explicit rules, they learn patterns and make predictions. This is the kind of computing behind things like voice assistants or image recognition. Then there are hybrid systems, which try to combine the best of both worlds. They use symbolic reasoning for structure and logic, and subsymbolic learning for flexibility and pattern recognition. These are especially useful in more complex, real-world applications where both logic and learning are needed. The image on the slide shows how these systems are built and what kind of results they produce, giving a visual sense of how each approach works in practice. On the left, we're looking at what's called supersymbolic computing. This goes beyond traditional symbolic or neural network-based systems. Here, we're modeling knowledge at the system level, so not just data, but how systems behave, adapt, and even self-organize. It's inspired by GTI and includes things like IaaS, POS, and how workloads behave. What's really interesting is that it brings in ideas from cognitive science like embodied and extended cognition, so the system is aware of and interacts with its environment. On the right, we see how these systems actually operate. The key idea is that knowledge isn't just stored, it flows and evolves. Programs, memory, and functions are all treated as knowledge structures. The diagram shows how the system moves through time, tracking its current state and past states while an intelligent processor coordinates everything. And it's not just smart, it's autonomous, self-replicating, and even has a kind of metabolism to manage its internal resources. So overall, this slide shows a shift from traditional computing to systems that are more like living, thinking entities driven by knowledge, not just code. This picture illustrates how the general theory of information, GTI, underpins the flow from raw information to intelligent applications. Information inputs includes data structures, algorithms, and multimedia, text, audio, video. Computing models, symbolic and subsymbolic computing, process this information through execution, machine learning, and deep learning. Knowledge formation leads to domain-specific digital genomes and supersymbolic computing, forming autopoietic and cognitive knowledge structures. Applications: these knowledge structures power advanced systems like robotics, transformers, and general AI. Knowledge network features: supports associative memory, advisory systems, scientific explanation, and event-driven transaction history. This flow shows how GTI enables the transformation of raw data into adaptive, intelligent systems. This slide shows how GTI is used to build a smart, self-managing video streaming system. Basically, the system can organize and regulate itself kind of like a living organism. It learns from past events, adapts in real time, and keeps things running smoothly without needing constant human control. The diagram shows how different parts like the digital genome, cognitive and autopoietic functions, and cloud resources work together to make this happen. There's also a demo link at the bottom if you want to see it in action. This slide shows how GTI is applied to build a smart medical assistant system. It's designed to be self-regulating, meaning it can adapt and manage itself without constant oversight. It uses memory and past interactions to learn, stay aware of the situation, and adjust its behavior. The diagram highlights how a patient and care provider interact through a digital assistant that combines symptoms, expert knowledge, and treatment options to help bridge the gap in understanding and improve early diagnosis. There's also a link to a video demo if you want to see it in action. Watch here. George Dyson points out that metabolism, energy use, and replication, self-copying, are logically separate. That means we can imagine machines that do one, the other, or both, just like biological systems. The key idea here is that by combining symbolic computing, structured logic, with subsymbolic computing, like neural networks, and managing energy and entropy, we could build machines that are both energy aware and self-replicating. That's a step toward general intelligence. The diagram ties it all together, showing how code, data, and resources, guided by best practices, can support this kind of intelligent system. It's a vision of machines that don't just compute, they evolve, adapt, and sustain themselves.